our last presentation of the day.
It'll be Dean once he gets the microphone working.
Maybe so, yeah. One with a nicer clip on it at least.
So,
Okay, I got it. No, I got it. I think I got it. Normally I'm helping people do technology stuff.
Dean Hardy from Geography.
Okay, awesome. All right, so just a point of clarity here in my title. I'm talking about states, and for those of you who haven't read the abstract, I'm talking about nations, nation-states, countries, not Georgia, Florida, South Carolina. And I'm going to talk to you about global sea level rise and some preliminary analyses that Brian and I have been working on. And Brian's here, he's a postdoc in Warnell. The talk goal is to answer these three questions. How does observed sea level rise compare to committed sea level rise? And I'll explain the difference in a minute. Who's responsible for the sea level rise commitment we've already achieved or reached? And how does that responsibility change out into the future? So a crash course, given the speed of the talk, we know that we've released about a little more than 500 billion tons of carbon into the atmosphere since the mid-19th century. And we also know the relationship between carbon emissions in the atmosphere and atmospheric temperature to be about 1.6 degrees per trillion tons of carbon released. We've observed about a 0.8 degree Celsius increase in atmospheric temperature since the late 19th century, which meshes well with our understanding of the relationship. And in terms of sea level rise, we've seen a little more than 0.2 meters increase since 1880. And the relationship that's key to the results here in this analysis is for every degree of warming, land surface temperature warming in the atmosphere, we see a 2.3 meter increase. And this is all based on previous research I don't have time to go into the details for. So this is a graph showing years across the x-axis and sea level rise in meters on the y-axis. And the blue line is observed sea level rise, global mean sea level rise. And the purple line is sea level rise commitment. And this is a little bit challenging of a concept to get your mind around perhaps, but what this means is that given our understanding of the relationship between atmospheric temperature and sea level based on distant historical paleo temperature and paleo sea level using semi-empirical models, people came up with this 2.3 degrees per 1 degree temperature increase in the atmosphere. We've already committed to 1.8 meters. So the key from this graph is that if all emissions ceased right now, we would still see 1.6 more meters of sea level rise. And if we decide to parse that out and use recently published data on attribution of emissions and warming of the atmosphere to specific countries or regions, and here it's broken down into a few countries and regions, and this is based on work from Ward and Mahowald. It's broken down by Annex 1 and non-Annex 1. And that's a UN designation, basically meaning developed and developing countries. We can see just how much sea level rise each of these countries has committed us to already, if all emissions were to have ceased as of the year 2010. So our total, again, is 1.8. Developed countries are responsible for about 1 meter. For example, here the United States is responsible for 0.41 meters. And so our contribution to this, Ward and Mahowald did the temperature, and we just basically used that relationship between temperature and sea level based on paleo data. Now, if we want to project that out into the future, we can do that in lots of ways, but the way we chose to do it was to use two emissions, climate futures, or emissions scenarios as presented by the IPCC, the Intergovernmental Panel on Climate Change. And for those of you not familiar with this, so I've tried to walk you through this because it's complicated. Again, year on the x-axis, meters on the y-axis. Black are total projections for each of these two scenarios. RCP 8.5 being a high emission scenario. And for those of you who want to know, RCP stands for Representative Concentration Pathway. And RCP 4.5 being an intermediate low emission scenario, one of the 4 primary scenarios released in the latest assessment report from the IPCC. And to again highlight the difference between what we expect to see, which these are IPCC forecasts here, the area shaded in gray for those of you who can't see. So this is the high-end forecast that the IPCC has of from 2010 out to the year 2100 of about 0.8 meters. Our commitment to sea level rise grows much faster than what we expect to see because of a lag effect, right, between the warming of the atmosphere and the actual response of the global climate system. Now, to get into the blue and the red here, basically this is breaking down and allocating a level of responsibility to Annex 1 and non-Annex 1 countries or regions for each of these two scenarios. So if we add RCP 8.5, which is basically the commitment from developed countries, to RCP 8.5, the commitment from developing countries, we would get this total here. And one of the key points to take away from this graph is the changeover, the location at which this changes over. Now, these are kind of preliminary analyses, and so this changeover point is a little later than that found by Ward and Mahawald, who modeled this for temperature change and allocating that temperature change based on emissions to specific countries and regions. But the point is that that will happen at some point, that changeover, right? And here we have it as 2044. They had it around the 2020s sometimes, when if you were to total all of the emissions from developing countries, it would surpass the total emissions from developed countries. Now, so the crossover is important, but it's also important to take into account that this does not account for trading or outsourcing of emissions, so all of the stuff we buy from China, right? So none of that is taken into account in these calculations. And just very briefly, so you know that we've thought about it, some future directions are, being a little more specific about states, so breaking down some of the regional assessment and doing per capita calculations, and then assessing impacts. So if the United States is responsible for 0.4 meters, what would that actually affect? What does that mean? How many people is that 0.4 meters going to affect? And that's it. Thanks.